Hello, Willis.
Yes, I can hear you.
Okay, would you be able to read out the Leah citations, and then we can take it from there. Maybe before that, Leah, to introduce you to our group, we're a mixed group of galactic and extragalactic people of different levels, masters, PhD, and happily today we've got an honor student who's joining with me right here in my office.
Great.
Which is nice. We also have faculty members who are joining us as well. So it's a diverse team, which gives you an idea on how to probably explain more of some of the concepts better to galactic astronomers who may not understand some of it. And I think that's about it. It's quite a large group. Can already see probably 26 of us already online. So yeah, others may join later or may not join, or they are looking over the shoulders of their friends in the same computer. But again, thank you very much for accepting to speak to us. And Willis will now read out your citations, and then we can listen to the talk. Willis, please.
Yeah, thank you very much, Prof. So unfortunately, Leah didn't send us a bio. So I'll just read out what I extracted from the internet, which hopefully is okay. And it's now my pleasure to introduce Professor Leah Morabito, who is a radio astronomer at Durham University. She's a professor in the Department of Physics and the Institute for Computational Cosmology. She holds a UK Research and Innovation Future Leaders Fellowship, supporting her work on high-resolution, low-frequency radio surveys using the LOFAR, a Pathfinder telescope for the SKA array. Her research focuses on how supermassive black holes and their host galaxies evolve together, particularly through observations of active galactic nuclei. She specializes in low-frequency radio imaging and data analysis to understand the role of black hole activity in shaping galaxy evolution. Professor Morabito earned a PhD in astronomy from Leiden University and a Master's of Physics with emphasis in astronomy from the University of Oklahoma, and a dual Bachelor of Science degree in Physics and Astronomy and Astrophysics from the University of Michigan. She previously held research positions at the University of Oxford. Thank you very much, Leah, for accepting to speak to us today on the highest resolution at the frequency and the lowest frequencies, what LOFAR can tell us about AGN. Welcome.
Thank you. Thank you, Willis, for the nice introduction. And thank you for having me to speak to you. I'm very honored to have this invitation and to get to share with you today what I've been working on. So Willis gave a very nice introduction to my background, but just to give you a little visual to go along with that, I like to start off my talks by saying I'm a radio astronomer by trade. So if you've seen the movie Contact, which is actually the movie that made me want to become a radio astronomer in the first place, you know, I like to think of myself as like the Jodie Foster character. But instead of the VLA, I primarily use a telescope called LOFAR. So we will talk about LOFAR and what it is in this talk. And hopefully that will be interesting to everyone, regardless of what kind of science you do, galactic or extragalactic. And hopefully I can explain things at a level that keeps the galactic astronomers on board, because this will be a talk focusing on extragalactic. So to just give you a little bit of setting the scene and tell you what AGN are, or active galactic nuclei. An active galactic nucleus is powered by a supermassive black hole at the center of a galaxy. We think that every galaxy has a supermassive black hole. The Milky Way, for example, has one, but they're not always active. So on the left here, you see an artist's rendition of the kind of like central tons of parsecs around this supermassive black hole in an active galaxy. So this galaxy is actively feeding on the material in it. And so that material is coming down, and what happens is it all tries to accrete onto the black hole, but it can't do that all at once. The material has some sort of angular momentum. And so what ends up happening, just like you're watching water go down a drain, it can't all do it at once, and so it sets up into this swirling disk. So this is what we call an accretion disk. Because all the material is coming together and compressing, it's getting very, very hot, and so it generates black body emission, which comes out in the optical to UV. So on the right, you see what this is the the overall spectral energy distribution of what we would see from an active galactic nucleus. So you can see this bump here in the optical to UV. So surrounding this this region, then you have this this kind of like donut shape, which is made of dust, and we call this a dusty torus. Oh, sorry, I've completely gone the wrong way. So let me just yeah. So the dusty torus. So the dusty torus takes the emission that's coming off of this accretion disk, this optical UV emission, it absorbs it, and then it re-radiates it in the mid-infrared. And so you end up with this this bump in the infrared. And that tells you that there's a torus there. And then spoilers already, the corona is just diffuse gas that sits above this disk, and that is very, very hot, very diffuse gas, and that comes out in the X-ray. There is a soft excess in the X-ray. We don't really understand where this comes from, but that's not the focus of this talk. We're going to talk about radio today, so I'm not going to talk more about all the different components of the X-ray spectral energy distribution. And then finally, the missing piece of this picture is the radio. So about 10% of galaxies have an active galactic nucleus at their center, and in about 10% of those that are active, we see relativistic jets. And these emit synchrotron emission in the radio. So this is what you would see on the right-hand side here. In terms of the radio spectral energy distribution, you'll notice there are two lines there, and we will come back to why there are two lines later on. So this just gives you kind of an overall idea of what the spectral energy distribution looks like. So this is what an AGN would look like to us if we go out and observe it across all these different wave bands. Because, of course, we can't actually resolve all of these components because this is the central tens of parsecs of a galaxy. So why do you care? Or why do I care, at least? Well, AGN are very interesting because we know that they co-evolve with their host galaxies. We know this both from observed relations. So on the left-hand side here, you can see that this is a correlation between the supermassive black hole mass and the galaxy velocity dispersion. So supermassive sounds really, really big, but it's actually a tiny, tiny fraction of the overall galaxy's mass. And so the fact that there's a correlation between this tiny piece of a galaxy at the very center of it and some global property like the velocity dispersion of stars in the broader galaxy is actually really significant. So this is indirect evidence that the black holes and the galaxies are co-evolving. They're somehow related to each other and they know about each other. Otherwise, you wouldn't get such a tight correlation. We also know from cosmological simulations, so again, indirect evidence, that we have to have AGN in these simulations to be able to reproduce the observed properties of galaxies. And so this figure here on the right shows you the space density of galaxies as a function of their stellar mass, so how big they are. And on the orange curve there is just what you get if you just predict the galaxy distribution from lambda CDM. And you can see that it doesn't agree with the observations, which are the gray points, either both at the low mass end and the high mass end. The low mass end we're not going to talk about in this talk because that's really coming from stellar feedback. So the simulations need things like stellar winds and things like this to help drive that orange line down to the data points. On the high mass end, we know that we need AGN, so you have to put a black hole in the center and it has to be able to interact with this galaxy somehow for us to be able to reproduce the observations in simulations. So this is why AGN are really interesting, because they are a key component for understanding how galaxies, the population of galaxies that exist in our universe. So they've helped shape the galaxy evolution. So in this talk, it's divided into several sections. So this is what we'll cover. We'll first talk about the radio emission that you can get from AGN, because this is a radio-focused talk. We'll talk about AGN in radio surveys in general, and then we'll talk a little bit about the International LOFAR telescope, and then looking at AGN with LOFAR VLBI, very long baseline interferometry, and finish up with ongoing work and future plans. Okay, so starting off with radio emission from AGN. So there are two main types of radio emission. You can get synchrotron emission, which is from electrons accelerating in magnetic fields. and you can have free emission, which is from electrons accelerating in an ionized medium. So the difference between these really is that synchrotron, you require magnetic fields, and in free emission, you just have ions. You don't have magnetic fields, but you do have ionized particles that are causing those free electrons to change their path, which produces the radiation. So this is an example spectral energy distribution for M82, which is a nearby galaxy, flux density versus frequency, and you can see the different components of the radio here. So the orange is the synchrotron emission, and then the green here is the thermal or free emission, and then over here you have dust, which has nothing really to do. You're starting to get into the infrared there is not part of the radio. So in this talk, we're going to focus really on the synchrotron emission because we're going to be talking about low frequencies. So you can see on the x-axis there, frequency, that the free emission really cuts off above or about 1 gigahertz, and we're going to be talking about things at lower frequencies. So we're really going to only focus on synchrotron emission. So that's the kind of radio emission, but where is it coming from? Oh, right, first, why are low frequencies important? So by going to low frequencies, we can do several things. So this is just an example of the bands for the LOFAR telescope, which is low frequency, and things the Very Large Array, which is the telescope that Jodie Foster's character used in the movie Contact. So at low frequencies, you can see that the synchrotron spectral index is it goes up, right? It's a power law. So things are brighter at low frequencies, which means that you don't have to build such a sensitive telescope to be able to see the same object at 100 megahertz as you would have to build to see the object at 5 gigahertz, for example. It's the only way to measure low frequency absorption. So you can see in both of these radio spectra that you get this turnover at low frequencies, and these are just simulated example spectra. So you can have synchrotron self-Compton or free absorption. It doesn't really matter what the physical process is. The point is that this absorption happens at low frequencies, and you have no idea that it's happening if you just observe with the VLA. So you have to go to low frequencies to observe that absorption. And then you can also probe lower rest frequencies for high redshift sources. And so this is where it comes into play that there's a redshift 0 source here. And then if you take that source, that solid line, you take that radio spectral energy distribution for that source and you redshift it out to 2.5, you can see that everything shifts over, which just exacerbates the problem of trying to detect it at higher frequencies, trying to understand what's going on in it at higher frequencies because of the redshift. And so you really, to probe the higher redshift population, you really need to go to lower frequencies as well. We won't really talk about spectral modeling or spectral aging in this talk, but just so you're aware that the higher frequencies can be affected by spectral aging, which causes that spectrum to have a high frequency turnover. And in order to understand how turned over it is, which corresponds to the age, so how old that plasma is, you have to be able to measure what the initial power law was, which means that you need low frequencies. Okay, so specifically in AGN, what could produce that radio emission? There are a few different possibilities, which are outlined here. And the first one is the corona. We're not really going to talk about this because this is really not expected to be a big impact. It's a very minimal kind of, at least in the majority of populations that we're looking at, it's really a very small fraction of the radio emission that's present. Oh, I'm going the wrong way. There we go. Okay, so the first thing that can happen is star formation, right? So AGN live in galaxies. Galaxies form stars, and stars produce supernova remnants, and supernova remnants have magnetic fields. There's free electrons, and so you get radio emission. We know that radio corresponds to other tracers of the star formation. So for example, the radio far infrared correlation comes about because the far infrared is related to star formation through H2 regions, and the radio is related to star formation through radio emission from supernova remnants. So we know that star formation happens in galaxies that host AGN, and so you can have radio emission from star formation. Another possibility for radio emission in AGN that's more directly related to the AGN itself is radio emission in shocks from outflowing line-emitting gas. So what happens here is your AGN at the center drives some sort of wind. This goes out into the galaxy. It shocks the interstellar medium that's there. And when you have this shock front, you get radio emission from that. So you have magnetic fields, you have free electrons, and then you get radio emission. And then finally, you could also have jets. And so these are usually relativistic. They can be very highly collimated. And here's just a couple different examples. And for those galactic astronomers in the audience, let me just tell you a little bit more about jets, because we say the word jet, but we don't actually always mean jet. So here's those, sorry, my dog is barking. So here's those radio jets that are blown up, but actually the jet is not the whole thing here. So these are two different types of radio jets. So we have a Fanneroff-Riley type 1 source on the bottom and a Fanneroff-Riley type 2 source. So there's different components to this. So in the Fanneroff-Riley type 2 source, you see these very long, thin collimated structures. And so these are coming out from this little blob at the center. So this is where your supermassive black hole will be. And the galaxy itself is not much bigger than that. So that supermassive black hole is powering these relativistic jets that are very, very strong. They go out like pencil beams. And those are the actual jets. At the ends of these jets, so which is where the jets terminate, we call these hotspots or working surfaces. And you get like a high concentration of radio emission there. And then you have what we call lobes. And so you get this radio emitting plasma kind of flows back, and it starts to fade because it's aging. And so these are what we call lobes. Even when we don't see these very thin collimated structures, which we know are actually the jets, we tend to call these sources jetted sources, or refer to the whole thing as jets, because we know there are jets there that's causing all of these hotspots and lobe emissions. So that's what I mean by when we say jets, we don't necessarily always specifically mean jets. So just to make the comment here that these structures are like hundreds of kiloparsecs. So these extend far beyond the galaxies that host the supermassive black holes. With the FR1 source, you have something that's a little bit different. So you do have jets there, but they aren't as collimated. And so they kind of more like, if you turn on a garden hose, FR2s are going to be like a really high power pressure hose. And FR1s are kind of like a slower trickle out of a garden hose. But then you end up with these really diffuse structures as the material goes away from the FR1 there. We think these morphology types are related to the mode of accretion, so how the black hole itself is accreting. So this is a figure from a seminal paper in 1996 by Ludlow and Owen, which shows radio power versus stellar mass. And the FR2s are labeled on here as 2, and the FR1s are labeled on here as 1. And you can see the 2s are up towards the top of the plot, and the 1s are down towards the bottom of the plot. And so people thought, aha, okay, well, FR2s are really bright, FR1s are not, but this is also related to stellar mass because you don't draw a straight line across a horizontal line across this, and there's a division. And so people came up with this picture where the artist rendition that I showed you at the beginning, where you have this accretion disk and you have a dusty torus, we call that a radiative mode AGN. Also can be called cold mode, high excitation, or radiatively efficient. And so that is where you have this accretion disk that's very, very bright. These were thought to really be related to the FR2s. And then people thought, okay, well, when you don't have an accretion disk, what you have is what we call jet mode AGN, or hot mode, low excitation radio galaxy, or radiatively inefficient. So there's no accretion disk. What you have is you have hot gas that's coming down and chaotically accreting onto the black hole. This is called advection dominated accretion. And so it's not the same picture as I presented at the beginning, because you don't have this accretion disk, you don't have this torus, you don't have this hot corona in the X-ray. You just have hot gas that's coming in and just like cramming onto the black hole every which way. And so that was thought to be related to FR1s. So a comment on another classification scheme for radio AGN. So rather than FR1s versus FR2s, which is really talking about radio loud sources, people also divide things into radio quiet and radio loud. So coming back to that spectral energy distribution from the beginning and looking at those two different lines. So when people first went out and started looking at radio sources, they thought, okay, well, let's take the ratio of the radio luminosity to the B band luminosity, which you can see in the spectral energy distribution, is the ratio of how much power is coming out in the radio in those jets to how much power there is in the accretion disk. And so from this paper from 1989, great, look, we have two samples, right? A bimodal distribution, because astronomers really like to put things, say that things are bimodal. And you can classify things as either radio loud, so they have a very high ratio of radio to B band luminosity, or radio quiet, which means that they have a very low ratio. And people thought, great, this is an excellent way to pick out those sources with those really big, powerful radio jets that extend out to hundreds of kiloparsecs. We can just put a line down the middle and say anything on the right is this, like, you know, these Fanneroff-Riley type sources. Anything on the left is radio quiet. Well, we built the VLA and then we started doing surveys with it, and then the picture got updated. And so here's a paper from 2007 using data from the faint images of the radio sky at 21 centimeters, our first survey. And now here's the same distribution of radio loudness. And you can see it's just a continuous distribution, right? So now that you're observing many more sources, you can see that you have your radio quiet population here, and then you have this really long tail. But just saying R greater than 10 is radio loud is not really doing a good job at dividing two totally separate populations, because in this radio loudness parameter space, they really overlap. So just to make a comment on this, a high enough cut, if you take a high enough radio loudness cut, will ensure that you have a very clean sample of things with really powerful jets. So if I move this purple line over to, say, 100, then I know that everything to the right of that is caused by really powerful Fanneroff-Riley type jets. But that's a very clean sample, but it's not very complete. So if you start, the more you start shifting that line over to the left, the more complete your sample will be, but you'll get contamination from the radio quiet population, which you can see here is something different, right? And so I just want to point out for people who might not be radio astronomers or familiar with this, that quite often in the community, you'll hear the term radio loud. And what people really mean by that is jetted AGN, or AGN with these really powerful large scale jets. And that's really misleading, because radio quiet is often taken to be the converse, as like not jetted AGN, but that is not necessarily true. And one of the major open questions that I am trying to answer is what actually is generating the radio emission in these radio quiet AGN, because we really don't know. It's very easy to go out and observe and see these really loud, really large, powerful jets, but the radio quiet population, we don't really know what's happening there. Part of the problem with that, and why that's a big open question, is spatial scales. So you have scaled all the way from the nuclear region, which is like less than 10 parsecs, out to galaxy cluster scales, which is up to a few megaparsecs. And processes can happen on all of these scales that produce radio emission. So on the scale of the galaxy, so the nuclear region, the galactic disk, you can get star formation, and you could potentially get radio emission from winds from AGN. And then on all scales, you can get jets. So jets can go out up to galaxy cluster scales. We have observed jets up to a few megaparsecs even in size. And so you can, it's very easy to take a look at these kind of like larger scale sizes in the radio, because that's where most radio surveys provide enough resolution to actually understand what's going on. Okay, so let us take a look at some AGN and radio surveys. So to give you a little introduction to radio surveys, typically they have up to a few arc seconds in resolution. They cover large portions of the sky. They can come at a wide range of frequencies. So we will continue to kind of like dive into the low frequency side, but there are many surveys at higher frequencies. So this figure on the right here shows you resolution versus frequency. Because radio emission produces a power law, you want to compare sensitivity for that power law. And so everything here has been scaled to a single frequency, which is 144 megahertz. And you can see the sky coverage of as the size of the colored points. So the first survey, which is probably, if you're not a radio astronomer and you've heard of a radio survey, you've probably heard of this one. So this is the faint images of the radio sky at 21 centimeters, which was conducted at 1.4 gigahertz, has about 5 arc seconds resolution, and pretty good sensitivity. I have primarily worked with LOTS, which is the LOFAR 2-meter sky survey, so using the LOFAR telescope, which we'll talk about in a minute. This is at 150 megahertz, 6 arc second resolution, so comparable resolution to FIRST, but it is deeper. So it has a sensitivity that's about a factor of 2 in terms of absolute numbers, but when you take into account the different frequencies that these surveys are at, LOTS is about 10 times deeper than FIRST for a typical source with a typical spectral index. So I mean, it's first. So if you take nothing else away from this talk, my plea to you is, if you want radio information and you're not a radio astronomer, you should check out the LOFAR 2-meter sky survey rather than or in addition to FIRST, because it's more likely that you will find a radio detection for your source in there. So there's well over 300 science papers using LOTS data, and quite a lot of those are focused on AGN. So one of the major results I think that's come out of the LOFAR 2-meter sky survey is looking at these jetted AGN, so those Fanneroff-Riley type sources, and looking at how the morphology, FR1s and FR2s, are related to accretion mode. So I introduced that picture in the beginning where we think that cold mode accretion, or that typical accretion disk picture that I presented, is associated with FR2s, and that chaotic accretion or hot mode accretion is associated with FR1s. So Beatriz Mingo took a look at the LOTS deep fields and looking at FR2s and FR1s, and so and what kind of accretion mode that they have. So finding from the optical spectra what things are high excitation or radiatively efficient or cold mode accretion, so have an accretion disk, and compared that to what she saw for the morphology for these radio sources. So here you have radioluminosity versus star formation rate, and this is the orange sources here are your FR1s, and then the blue and the red sources are your FR2s. And so, and things that we think that we can identify as having an accretion disk are outlined with these black diamonds. So what came out of this is that you'll notice that all of these black diamonds are towards the right of the plot. What came out of this is that actually it's not related to the morphology. The accretion mode is linked to the specific star formation rate. And the morphology, which has been seen in simulations. So Nicole Thomas, who is a postdoc with me, but is now a fellow in Australia, Nicole Thomas has already also seen this in simulations. So that's quite interesting. So it may be that this picture that cold mode accretion produces FR2s and hot mode accretion produces FR1s may not be right. And then revisiting this plot again, Beatriz just made this plot, but with LOFAR data, and found a complete mix of the populations, right? So here you see the orange sources are FR1s, the blue are FR2s, and there's FR2s everywhere, and there's FR1s that are above the normal kind of cut that you would make to say that divides FR1s versus FR2s in terms of radio power. So there's a lot of low power FR2s that are now detectable in the LOFAR 2-meter sky survey that we didn't find before. And so this was really a critical thing that came out of radio surveys in the very near past. And so by looking at this in more detail, Beatriz was able to show that morphology is actually linked to stellar mass. So here's the FR1s and the FR2s. So when you control for radioluminosity, you find that the FR1s really are the high mass things, and the FR2s can happen at a wide range of stellar mass. But there are still some open questions from the studies, because this was limited to resolved sources with 6 arcsecond resolution, because this was done with lots. So this is radio power versus radio size, and you can see that there's kind of like area where there's not a lot of sources in there. And one of the remaining open questions to take this work further is, what about jets with lower power or smaller sizes? So we started seeing these lower power FR2s, but does this continue to extend down to lower powers? So this is one of the questions that we've been trying to answer with LOFAR data. Do jets extend down to lower powers? And you can do something quite clever. So you can say, okay, well, I don't have the resolution to see if there are jets at lower power things, which tend to not be these really large sources. And so I don't have enough resolution to see what's going on. So, but you can do is you can model the total radioluminosity as just a combination of radioluminosity due to star formation and radioluminosity due to AGN. And you just pick the radioluminosity for the AGN from a simple power law that goes all the way down to low radio powers. And then you can say, okay, well, I'm just going to optimize this for all of the galaxies in my study, which is something like tens of thousands of galaxies, and see if you can match the observations. And so a master's student started this work and has been since picked up by a PhD student at Edinburgh, who found that yes, you can reproduce the flux density distribution just using the simple model, which predicts that radio jets go all the way down to low powers. The other nice thing is that you do that, and then you also find that you can reproduce the radio loud population. So I said at the very beginning that only about 10% of AGN have radio jets or are radio loud. And so this model also reproduces that fraction, that 10%, which is great. And then if you look at the simulated data, so that's what this is here on the right now, you can see this y-axis is the ratio of the AGN luminosity to the star formation luminosity, radio emission. And so this is the line where you have equal parts coming from star formation and equal parts coming from AGN. And then here on the x-axis, you have the radio loudness parameter. And so this is the canonical definition of radio loud. So you can see that this definition of radio loud is doing a very good job at picking out these very powerful, clearly AGN-dominated radio sources, which is that jetted population, those Fanaroff-Riley type sources. But there's still this whole population here where they wouldn't be classified as jetted AGN because they're not radio loud, but they are still clearly AGN dominated. And so the question really here is, well, okay, so we found this population of radio quiet jets. What is going on with these? How can we identify these in surveys and study them? So we can also ask the question, even before we go out and say, okay, how do we find them and study them? We can also ask the question, do jets explain everything? So this is maybe a little bit confusing, so let me walk you through this. On the right-hand side here, we have what's called the carbon-4 emission space. So this is the carbon-4 emission line equivalent width on the y-axis versus the carbon-4 blue shift on the x-axis. And you can see this kind of curve in the space for all this data. So we know that the carbon-4 emission line is related to the AGN, and people quite often look at just the carbon-4 blue shift as the stronger the blue shift, then the stronger the AGN is kind of the idea. But there's been some work done that shows that if you actually follow the curve in this carbon-4 emission space, which we call the carbon-4 distance, this actually is a proxy for the Eddington ratio. So you have low Eddington ratio things down here, high Eddington ratio things up here. And this shows you some radio data that is overlaid. So you have things that are non-detections you have things that are detections, and you have things that are detected in first. And so we see that there's a difference in the low carbon-4 distance sources versus the high carbon-4 distance sources in terms of their radio properties. So things are more likely to be detected at high carbon-4 distance, which is what you kind of see in this figure on the left, where you see the radio detection fraction going up with blue shift. But you see that the radio loudness fraction is going down. So on the left-hand side here, and the kind of like top left here, this is what we think is jet dominated. This is where you have lots of radio loud sources, things that we can clearly identify as jets. But as you get down into this kind of like large carbon-4 distance values and large carbon-4 blue shift values, this is where the AGN is really wind or disk dominated. And so you have more radio emission coming out in this wind or disk dominated area, but these things are not radio loud. So where is that radio emission coming from? So my PhD student, James, who's now a postdoc in Leiden, tried to look at some things that have disk winds, so broad absorption line quasars. In their optical spectra, you see broad absorption lines, which are indicative of winds. It's about 10% of optical quasars, although there's larger fractions in the radio infrared. So on the bottom left here, you can see what these broad absorption lines look like. They're characterized by what's called the balnicity index, which basically tells you about the strength of the outflow. So you can have things that are low balnicity index and high balnicity index, and you can see examples there. So we know that there's a correlation between the balnicity index and the radio detection fraction. So the higher your balnicity index, the more likely you are to be radio detected. And James went out and looked at the absorption profiles for a radio and non-radio detected sources, and found that actually the absorption profiles look different. And that's what you see in the top right there. And then he followed that up with a study where he showed that also the higher fraction of radio detected things in the BAL population, things that have broad absorption line quasars, having a higher radio detection fraction is not entirely explained by color. So broad absorption line quasars, for various reasons, tend to be redder, and redness also has to, in their optical spectra, and redness has also been correlated with radio. But in the case of BALs, it's not enough to explain everything. So this is, again, that carbon-4 distance, which is the Eddington ratio from low to high. And you can see that the broad absorption line quasars, for example, are always in some of these bins, always have a higher radio detection fraction than non-broad absorption line quasars. So it's a very complicated picture, but we think that there is something to do with radio emission coming from winds. So that's the kind of like tentative conclusion here, and we need, of course, more data. So carrying on with winds, my other PhD student, Emmy, has looked at ionized outflows. So these are larger outflows. So these are galactic scale outflows, whereas the broad absorption line quasars are AGN driven, so closer into the center. So ionized outflows traced by the oxygen 3 emission line. So Emmy has gone out and looked at the things that are radio detected and things that are not radio detected, and then looked at the percentage of things with outflows, and found that radio detection, sources that have radio detections are more likely to have outflows. So that's also very interesting that you get higher radio emission with correlated with outflows on galactic scales. And we'd love to be able to say where that radio emission is coming from, but unfortunately we can't because these things are pretty radio quiet. They fall into this regime where we cannot tell if they have loud, really powerful jets. That's the only thing we can say, is that these sources tend not to have really powerful jets. And that's what this figure on the left is showing. This is radioluminosity versus star formation rate. This is kind of the main sequence of star formation. So that correlation between radio and star formation I talked about at the beginning. And then up here is where your Fanneroth-Riley sources lie, above this solid line, which is kind of like the top of the radio star formation correlation population. And so anything up here the radio cannot be explained by star formation. So this is really interesting, but we still can't tell where this radio emission is coming from. And that's where the International LOFAR telescope comes in. So the International LOFAR telescope is a phased array that operates below 200 megahertz, just around the FM radio band, has a very large bandwidth, flexible spectral resolution, and very wide instantaneous field of view. You can also do multi-beaming things because it's just dipole antennas, so they're not pointed mechanically, so no one's going out there and turning a dish to point it. You just point it by introducing delays in the signal path. So this shows you where these antennas are located. So we have dipoles, and there's examples of the dipoles there on the bottom left. These are collected into stations, and so each station has 96 dipoles for each of the LBA low band and high band antennas, and then those stations are spread all across Europe. Just to show you what these stations look like, here's a collection of 6 stations at the center of the array in the Netherlands. Okay, so flexible angular resolution, what does that mean? Well, there's many stations here, and if you use just the ones in the Netherlands, which we call the Dutch stations, so you have some core and remote stations there, and this is what's used for the LOFAR 2-meter sky survey to get you 6 arc seconds at 150 megahertz. So that's you can see that from the curve on the left-hand side there, which is resolution versus frequency. Okay, so 6 arc seconds with the Dutch stations. If you expand out to use the entire international array, you can then get 0.3 arc second resolution at 150 megahertz. So all of a sudden, you're beating the best you can do from the ground using adaptive optics on optical telescopes, which is just absolutely phenomenal. To give you a feeling for that improvement, which is about a factor of 20, here's an image up in the upper left-hand corner. Let's pretend this image was taken with the Dutch array. And if I improve the resolution of this image by a factor of 20, which is exactly what you do when you go out to use the international stations, then all of a sudden you can see it's my dogs. They're no longer blobs. You can see there's 2 of them. You can see they're different breeds. You can see they're sitting on chairs. They're outside. All these this kind of detail that you don't get with just the Dutch station picture, right? So this is the resolution improvement that you get by going out to the international stations. But there's many challenges, and I'm not going to go into all of them, but just to let you know that at low frequencies, the ionosphere is really our biggest problem. And I'll show you a video in just a second. Data volume is also a challenge because the data sets are very large. The stations are all on individual clocks, and so those have to be calibrated. And when we started doing this work using the international stations, we didn't know what good calibrator sources in the sky were to ensure that we could correct the errors in our antennas. And then also, once you start going to low frequencies, your source characteristics mean that you are struggling for signal to noise because you have low frequency absorption. You have no idea what the source structure is like at low frequencies. So just to give you a picture of what happens with the biggest challenge, which is the ionosphere, here's a video that shows the same part of the sky. It's a few degrees. It's quite a large few degrees square. It's quite a large part of the sky. And this is all of the sources in here are extragalactic sources. So they are galaxies. They should not be moving on the scale of this 8-hour observation. But you can see that they are. And you can see that the left-hand side, which shows you an observation on a night with bad ionosphere, that they're moving a lot more than they are on an observation with good ionosphere, which is the image on the right. Now, the really nasty thing about the ionosphere is that you can see in this movie that the sources are not all moving in the same direction at the same time or changing their brightness in the same way. And some of them are changing shape. And that is a really nasty problem to correct, because that means that you have to make different corrections in different directions in the image. So you have to do what's called directional dependent calibration. You have to divide the image up, and you have to calibrate the data in such a way that you can get corrections for different directions in this very wide field image. And that's what makes a LOFAR so challenging. Click. I can go to the next slide. Right. Okay. But I won't bore you with the details, but we have solved this problem. And so this is what happens when you, before you calibrate for the ionosphere on the left, this is the best you can do. And then if you go back and do directional dependent calibration, you can get the image on the right. So this is exactly the same part of the sky, just before and after ionospheric calibration. And you can see that we can do it. But this was the work of many years to get to that point. So that was this is an example with the Dutch array. Calibrating the international array is built off of the calibration of the Dutch array. So the first thing that we do when we want to expand from 6 arcsecond resolution out to 0.3 arcsecond resolution is we actually just calibrate the Dutch array. And then from there, we use the LOFAR VLBI pipeline, which then uses some techniques to find solutions for the total electron content, or basically how we characterize the ionosphere for the international stations. So then we go out and we calibrate the international stations. We do an initial calibration for a single in-field calibrator source. And then from there, you can go off and do wide field imaging and do your directional dependent calibration. This is a very oversimplified picture. The LOFAR VLBI pipeline will get you calibration in very specific directions. It's very computationally cheap. It's a very nice application for wide area surveys. Here's an example on the left where you can just pick out and make smaller data sets for just a few sources and just image those at really high resolution. Doing wide field imaging where you get about 6 square degrees all in a single field. This image here has 7 billion pixels in it. But you get 0.3 arcsecond resolution across that entire image, and that is very computationally expensive. But we are working on it. And so we have processed several of the LOFAR deep fields. So these are fields where we have really good information at like optical, near infrared, et cetera. And so we really want to get the best information we can at the radio, which is the high resolution radio information. And so this is what you get with that sub-arcsecond resolution. These are real sources. The GIF on the left is fading from the 6 arcsecond resolution down to the 0.3 arcsecond resolution. And you can see that all of a sudden, we can see all the detail in these AGN sources, which is just absolutely fantastic. And on the right, you can see an example of where you have a galaxy, you have radio emission, you have no idea where that's coming from. And then when you start to resolve it, you can see there are galactic scale jets, which is absolutely great. So you can start studying those low power, smaller size jets now as part of the whole jetted population. The other thing that resolution gets you is accurate source identification. So here's a source, which we thought was a wide angle tail galaxy, just a standard Fenneroff-Riley type galaxy that's been bent by falling through a cluster. One source in the LOFAR 2-meter sky survey. And if you reimage it, all of a sudden you see, oh, wait, hold on, it's 3 sources. So here you have an FR2, you have an FR1, and then you have another point source. And the nice thing about this is not only can you disentangle cases where one source turns into 3, but then you can also accurately identify the optical counterpart for each of those radio sources. So if you're interested in learning more about high resolution with LOFAR and kind of what it gets you, there's a QR code for a review that's now published about the last decade of work that's gone into it and what we can do now. Okay, well, all right, I'm going a little bit slowly. So I don't have a whole lot more, but I do just want to talk about one really cool thing that you can do when you're looking at AGN with this high resolution imaging. So if you are familiar with VLBI or very long baseline interferometry at high frequencies, you may have heard of brightness temperature identification of AGN. And so this is the idea that star formation can only produce an upper limit. There's an upper limit to what surface brightness of radio emission that star formation can produce. And so if you detect something above that limit, then it has to be coming from an AGN. It can't be due to star formation. So this limit for star formation, which comes from models, is frequency dependent, and at gigahertz frequencies, you need milli-arc-second resolution to get enough surface brightness sensitivity to be able to identify AGN. But you can do this with 0.3 arc-second resolution at 150 megahertz, which means that you can now do this brightness temperature identification of AGN with LOFAR. So the real power here is not just that you can do this, but the fact that LOFAR has such a wide field of view. So if you look at wide field VLBI for AGN identification at gigahertz frequencies, here's EVN observations for the Hubble Deep Field. Only 3 AGN were identified in 5 arc minutes square field of view. You can expand this field of view using multiple simultaneous phase center observing, which is a very technical radio thing. You can expand this, and then with about 20 hours of data, you can identify 31 AGN with the EVN at 1.6 gigahertz. Great. But with LOFAR, a single 8-hour observation, you can detect over 9,000 sources in this 5.6 degree field of view. And then it turns out that you, instead of 31 AGN identifications, you're now getting about 1,600. So this is really the power of LOFAR, because it really moves you into being able to do population studies. So 31 for 20 hours versus 1,600 for 8 hours of observations. And the nice thing about LOFAR is that you can use the fact that you get resolution. You can image with just the Dutch array and get 6 arc-second resolution, which gives you the total emission from a galaxy. You can then image at the high resolution with the international array and get the AGN emission identified via brightness temperature. And if you subtract the one from the other, then you get the star formation emission. So you can start to separate out the radio emission from AGN and star formation and really try to understand how much are AGN contributing to the radio emission down here where we expect things to be star formation dominated. And so that's what I did in a very recent study looking at radioluminosity functions, where rather than looking at the typical radioluminosity functions, which are shown here on the left, where you say, okay, this galaxy is an AGN galaxy and this galaxy is a star forming galaxy, and I'm just going to do a radioluminosity function for AGN galaxies, a radioluminosity function for star forming galaxies. But if you can separate out the AGN and star formation radio emission, you can do radioluminosity functions by the process, so star formation versus AGN activity, rather than the overall galaxy classification. And then by comparing these two, you see what pops out is that at these low radio powers, if you divide one by the other, at these low radio powers, you see that actually there's about 50% more AGN activity than expected. And this is in a redshift range of 0.5 to 2. So this comes back to those low power jets potentially that we saw in models earlier on. There's really like a lot of radio emission that's coming from AGN activity at lower radio powers than we previously thought. So just to finish up with some future plans and ongoing work, we are now working on post-processing the LOFAR 2-meter sky survey to include the international stations. Data release 1 is expected this year. And in this figure, which we saw earlier, that moves the LOTS down to LOTS high resolution. You don't get much more increase in sensitivity, but you do get a huge increase in resolution. And we are only targeting, we're doing postage stamp imaging of just select sources. And so the sky density of sources won't be that great compared to other surveys, but it will be the first kind of like northern sky 0.3 arc-second resolution survey. In the high resolution landscape, LOFAR will still be really relevant. So this shows you resolution versus hours per square degree for a variety of surveys. And one thing that I just want to point out is that with LOFAR, we will get better resolution than the square kilometer array at similar frequencies, which is fantastic. And we will be more efficient for surveys than dedicated high resolution instruments with like the EVN. So LOFAR really sits in this unique space where this combination of high resolution and wide field of view will make it really relevant even going into the era of the SKA. And so things that we're working on now is making the data reduction more accessible. We're looking at polarization. We're looking at extending to the LBA, because all of the results here I showed you were with the high band antenna, and doing wide area and deep field surveying. And for that, I am PI of the LOFAR 2.0 ultra deep observation, which will look at the Euclid Deep Field North and be the deepest ever radio survey. And we're expecting to see AGN all the way out to redshift 6, and star-forming galaxies really out to kind of redshift 4. We'll get a source density of a sky density of about 75,000 sources per square degree, which makes it comparable to something like the Hubble Deep Field. So this will be a really incredible radio survey. And so I'll just finish there. I don't really have a nice like point-by-point summary, but I just want to say that LOFAR high resolution imaging is really becoming more mainstream. A lot of that is thanks to all the people you see on the slide here who have been working on this for the last decade. And we're really just scratching the surface with what we can learn about AGN. So stay tuned in the future. And I'm very happy to take your questions.
Oh, well done. Thank you very much, Leah. That's quite a very interesting talk. And I'm sure people who listened have really enjoyed it. I'll open up the floor for questions for you. Any questions?
Maybe I can stop sharing just so I can see people.
Yeah.
If I can figure out how to do that. There we go.
Let me see if there are hands up. None yet. Anyone with questions for Leah? Maybe while you're still thinking about that. Oh, okay, Stabile. Go ahead.
Hey, Leah, thank you very much for that very comprehensive and just informative and colorful talk. So, yeah, as far as that, the whole star formation and AGN classification, that kind of debate. So you've introduced, of course, the brightness temperature method as a way of tracing the actual physical processes and being able to disentangle the AGN and star-forming galaxies. Just from your own kind of philosophical view, is the multi-wavelength classification something that we should kind of continue to take with a pinch of salt, or can we trust it, I guess, going forward as we have deeper multi-wavelength photometry coming from surveys such as that of LSST, Euclid, JWST? What's your thought on that going forward?
Yeah, well, I mean, my thought is, yes, it is a philosophical question. And I think the more data, the better, because it gives you different information. I think the real power of being able to do this at radio is that radio emission is unaffected by dust. And so if you can separate the AGN activity from star formation across all redshifts, then all of a sudden you can do things like look at the cosmic star formation rate history, but unbiased by dust corrections. If you're looking at the UV optical, and unbiased by AGN contamination from if you're looking at the infrared picture. So you can get an unbiased tracer of star formation across a wide range of redshifts, basically, which you can't do at any other wavelength. And I do think that this is complementary. So you always want to put this information in context. You will always need multi-wavelength information, for example, to get the redshift for something, whether it's spectroscopic or photometric. But the ability to do this identification at radio opens up doors that multi-wavelength information does not.
Okay, cool. I've seen the hand from Paul Fallon.
Thank you for a very interesting talk. Really did appreciate it. You mentioned something about polarization data will be coming in a sort of sometime in the future. What are you expecting, or do you have any sort of key expectations as to what this would tell you once you've got the polarization information?
Oh, well, that's a good question. I'm not a polarization expert, but I mean, there's different science cases, of course, for polarization. So one thing that people are doing with LOFAR at the moment is actually looking for circularly polarized sources. So people are doing searches for exoplanets. So when you have an exoplanet and you have an interaction with a star, you get ECMI, which is electron, cyclotron, maser instability. And this produces highly circularly polarized radio emission, which peaks at low frequencies. And so you need something like LOFAR to be able to see it. So people are doing things like looking for that. And then there's also people who are doing studies of polarization in Fanaraf-Riley type sources, looking at polarization in the hotspots. There you get linear polarization. The nice thing about the high resolution is that you don't have to deal with as much beam depolarization. So if something has, a polarization fraction of only a few percent, you may not see it if you're looking through your surveys that have, a resolution of like 6 arc seconds or 20 arc seconds or something like this. But when you go to 0.3 arc seconds, if there's polarization in a compact region of emission, then you should have a higher chance of seeing it because it will be less depolarized. Yeah.
Okay, thank you.
Thanks. Eliab?
Hi, Leah. Thank you for the very, very nice talk. So I'm wondering, in terms of the star formation rate density, you've shown that there's less star formation than we expect.
Yep.
So I'm wondering what the consequences of this is on the star formation, the history of star formation based on radio, because I think in the last 5 to 10 years or so, getting the figures, the numbers that we were getting from radio were slightly higher than the usual.
Yeah.
Take the number down or the plot down.
Yeah, that's a great question. So, I mean, I know things like Alison Matthews has done, looked at the star formation rate density and the cosmic star formation rate density and found, yeah, exactly what you're saying, right? That it's a little bit higher. I do think there is some contamination from AGN. So the thing I will say is this kind of like increase to 50% more AGN activity than previously thought does translate to a reduction in the radio emission from star formation, because essentially what you're doing is taking this radio emission that you previously thought was star formation and saying, okay, it's actually AGN activity. But because AGN are a small fraction of the overall population, the reduction in the star formation at those lower radio luminosities is not as impactful on the overall population. So you get a reduction of about 10% in star formation rate. Whether or not that's enough to explain the discrepancies in these studies that look at the cosmic star formation rate density with radio emission, I think is yet to be determined. So there's still a lot of work to do here, but I just haven't done it yet. But it's an excellent question, and it is something that I am quite interested in looking at.
Definitely, ask is someone working on this. It's definitely very interesting.
Yeah.
Cool. Any more questions? Leah, I've got 2 questions for you. One
Okay.
is on the science side. The other one is on the technical side.
Okay.
What do you expect in the VLBI end if you have to stretch the baselines? At what limits in baseline would you start to resolve out everything at that low frequency? Do you have any simulations for this?
No, that's a great question, right? Because people are also saying like, oh yeah, let's push it to 0.1 arc second resolution. Yeah. But the thing is that the sky becomes emptier and emptier.
Yeah.
And at some point it's just diminishing returns, especially to do things like wide field, right? Where you're just going to have, out of your 7 billion pixels, which turns into, 20 billion pixels because you do it high resolution. You're going to get like fewer and fewer sources. it's hard to do the simulations because at low frequencies, you're kind of seeing a different electron population than at high frequencies. So you can't just project high frequencies down to low and expect that it will work. Because things just aren't, you're not seeing the compact components, you're not seeing the hotspots, you're seeing more diffuse emission. And so I think that we just don't know, and we're not really, we could do some kind of simulation, but we really don't know. The thing I will say is that in these high resolution images, I think that we're still something like 80 to 90% of sources are unresolved. But I think actually it might be a really interesting question to ask how many of the sources are like unresolved, like what kind of sources are they? Are they hotspots, you know, that you're resolving, you aren't resolving the compact hotspot, or is it you know, a star forming galaxy at high redshift, or you know, what kind of sources are they, and would you expect them to break into different components, or would you expect to see them if you continue to increase your resolution? But I mean, there's not enough people working on this, and so that's not something that we've that's been high on our priority list to do.
Oh, cool. And is there still discussions going on? I did bounce the idea of getting LOFAR south in Africa, just down to stretch your baseline a bit. Is everybody? Is there anyone still talking about this now, or the upgrade has taken over the entire discussion space?
Yeah. So George Miley is still talking about this. So I was in a telecon with him earlier today where he mentioned it. I mean, I think it would be great, but I mean, honestly, it's going to be mostly a political decision. And by that, I mean, like, it would be great to expand the community, but it's not necessarily that people are clamoring for more stations, because like our data sizes are already really large. And we already have like, we already have more data than we can handle. So like trying to change the nature of that data.
Yeah.
But I mean, LOFAR was always designed to be something where it's a low kind of barrier for entry to become part of the array. So I mean, like something like the ELT, which costs like billions to build, a LOFAR station costs like, you know, a couple million euros, or at least it did last time I checked. And so it's really you know, a good way to get into you know, putting forward a little bit of capital and getting a huge return. Yeah. I think that's been one of the things I've really liked about the LOFAR community, because we've expanded into Poland and Latvia, and now like Bulgaria and Italy since I started in LOFAR, and it's been great to see the community expand, and I would love to see it expand into Africa. But yeah, I think that LOFAR 2.0 is kind of taking over everything at the moment, and we're not even sure how we're going to handle the data rate there. So adding more stations, is people are like, hold on, let's figure out how we can handle the data from these stations first.
And the pipeline performance, how's that going? I know the 3GC was still, the DD faceting was still some problems the last time we had conversations. How is the pipeline performing now?
Yeah, so I mean, the pipeline, I think, so okay, so the first thing I will say is this wide field image that I presented took 250,000 CPU hours to make, and that number is now down to less than 50,000. Okay. We are at the moment working on just the kind of like final steps to make the pipeline run end to end with no human intervention. And at that point, we will profile it properly, and then we will adjust the resource requirements in the pipeline. And then we will start looking at where the bottlenecks still are in terms of the actual like steps and components. But we think that we can get this number down even further. And for something like the LOFAR 2.0 ultra deep observation, when you're re-observing the same part of sky, and you already know like where your calibrator sources are, you already have a sky model for starting your self-calibration, you can actually cut out a lot of those steps. And so doing it like a really deep image isn't like, you know, 400 times 30,000 CPU hours. The number of CPU hours required for going deeper goes down. So it will take overall less time.
Oh, awesome.
But I don't have like better numbers to give you at the moment, but I will by the end of the year.
Okay, cool. Nice. Okay, is there any other question from anyone from the room? All right, then thank you so much, Leah. I see we got no other question. Thanks for the fantastic talk. We'll all keep in touch. Thanks so much. Thank you.
Thank you for having me.
Yeah, thanks.
All right.
All right. Ciao. Keep well.
You too.
Okay, bye everyone.
Bye.
Cheers all.
Cheers.
Again.